Hi, in this video, we are going to look at some interesting results on triangle concurrencies. What do I mean by concurrencies? It means when several lines are meeting at a single point, then three or more lines, if they meet at a single point, it's known as a concurrency. Those lines are concurrent at a point. And there are many concurrencies that you can see in a triangle. And these configurations are very common in Olympiad problems. So we are going to explore triangle concurrencies and we'll see Ceva's theorem. And using that, we're going to prove a lot of results, right? But before that, let's try and look at a simple brain teaser which tells us why are concurrencies important. So I want to start with a example that can help motivate the subject for you. So think about a situation where there is an inaccessible region. This is a region where you can't go inside, you can't see what is going on inside. This is basically, think of it as a covered region. You can't see what is happening. And there are two wires like this. Let's say there are two wires like this, AB and CD. And our job is to place a third wire in such a way that we have to bisect the angle that is formed by these wires. So think about this inaccessible region and we can't really see what's going on here. But imagine that they were extended and they meet at a certain point. This is your inaccessible region, which you can't see. I want a third wire such that it is on the angle bisector here. Imagine there is an angle bisector of the point of intersection of wires AB and CD. I want to decide how to place this third wire. So how would you go about solving this problem? You can't really see the angle. This region is totally invisible to you. So how would you go about placing a third wire so that it absolutely bisects the angle between these two wires, AB and CD? So that is the problem. And this is where we will be using the fact that there are concurrencies in a triangle. So how do we go about doing it? I will just rub off this place. What I will do is I will just randomly make a third line here. Let's say this line is EF, right? Place a wire wherever you want, however you want, which cuts both the lines AB and CD. Now what you have to do is look at this angle AEF and bisect this angle. Because this angle is visible, we can easily bisect it, and we can similarly bisect this angle CFE. And the angle bisectors meet at a point, and this point is, let's call P. This is my point P. This is the point of intersection of angle bisectors of AEF and CFE. Now you realize that if there was a triangle here, which was made by the wires AB and CD, I cannot see the vertex here, but there is a triangle that is formed. Let's call it point X. Triangle X, A. Actually, you can talk about triangle XEF, right? And this triangle's bisector will also pass through the point of intersection of the angle bisectors of these two angles, right? This is the point where concurrency becomes useful. We know that the three angle bisectors of a triangle are concurrent. Right? And because the three angle bisectors are concurrent, when you find the point of intersection of the two known angles, the third angle bisector will also pass through this, right? So we found one point P which lies on the line through the angle bisector of this invisible angle, right? Now, what is the next step? In order to actually find the line, we need 2 points. So I make another wire like this. Let's call this G and H. I repeat the same process and I bisect this angle and I bisect this angle. And I know that the in-center of triangle XGD will be here, which will be the point of intersection of these two bisectors. And therefore, this point Q also lies on the angle bisector passing through the point X, which was not seen by us, which was invisible. And now, therefore, I have 2 points which determine the line completely. I know 2 points on the angle bisector PQ, P and Q, which lie on the angle bisector of this unknown angle, and therefore I can find the line. So what we are using is we are using the fact that the angle bisectors of a triangle are concurrent, and using that we have solved this trick sort of a question. That is just one simple example of why concurrencies are important and how you can employ them in different situations. So what we'll start off this video with is Ceva's theorem, and this helps us prove concurrencies in triangles. Prove that three lines are concurrent, we can employ Ceva's theorem to try to do that, right? So let's draw a triangle, and I will tell you what the statement of the theorem is. A, B, C. This is my triangle, and let's say three lines passing from the vertices. This is line AL, another line BM, and another line CN. Let's say these three lines are concurrent. These lines that pass from the vertex to the opposite side and intersect the opposite side are known as Cevians. Because we'll be using Ceva's theorem, therefore these lines are called Cevians. So these are AL, BM, and CN. Now, the theorem says that AL, BM, and CN are concurrent if and only if it is the theorem is working in both the directions. The standard direction and the converse is also true. If and only if the condition is BL by LC times CM by MA times AN by NB is equal to 1. Now, if you have some difficulty remembering the condition, there is a very easy way to remember the condition. Don't write it like this as ratios. Just think of each side, start from BC, CA, AB. Go along the sides in a certain order. You can go in a clockwise order. And if you look at the side BC, that is being divided into segments BL and LC, right? What we will say is that the product of alternate segments is same. So what is the first segment? Let's say BL. This is my first segment. I will skip this segment and I will say alternate segment here is CN. So every time you will skip one segment and say the other one. So BL times CM times, you'll skip this segment and then you'll say the third segment is this one, times AN. This product, this is the product of alternate segments, should be equal to the product of the other three segments, which is obviously LC times AM times NB. So this way you can easily remember you are taking three alternate segments on the sides. Start from the BC side and take the BL segment, then skip this segment, take this segment, skip this segment, take this segment. The product of the three alternate segments is equal to the remaining three segments product. So that is the statement of Ceva's theorem. What we'll do is first of all do a quick proof of Ceva's theorem. So the way we do the proof is this. Let's draw a triangle A, B, C. I will draw my Cevians. Let's say this is L, another one is M, and the third one is like this N. These are my Cevians. They intersect at the point P. This is the point of concurrency of the three Cevians. And what I'll do is I'll extend the Cevian from B and the Cevian from C. So I will extend it out like this. And what I will do is I will make a line passing through A, which is parallel to BC. So I'll make a line through A parallel to BC, and they will intersect the two Cevians at 2 points, right? So what I'm saying is this line is parallel to BC. I'm constructing that, and I'm also extending the Cevians from B and C, right? And let's say the point of intersection here are S and R, right? Now, because of the fact that the line SR is parallel to BC, we get a lot of similar triangles in this figure, right? So, for example, I can say that triangle AMR is similar to triangle CMB. Think about it. AMR is this one, is similar to, I'm saying, CMB. Why? You can easily say vertically opposite angles, and you can also say interior alternate angles, right? Because the lines SR is parallel to BC, the angle ARM is equal to MBC by interior alternate angles. And also there is a vertically opposite pair. So therefore this is a similar triangle situation. And when we write the ratio of the sides, you get AM by MC is equal to AR by RB. This is our first result. Then another similarity that you can find is triangle BNC is similar to triangle ANS. BNC, look at BNC, BNC and ANS. Again, same thing, vertically opposite and interior alternate, right? Same logic. So from here, we'll write similarity condition. BN by NA is equal to CB by SA. That is our second result. Then we have a third similarity. Triangle CLP is similar to triangle SAP. And from there, we'll be able to write the condition CL by SA is equal to LP by AP. This is the third condition. And finally, a fourth similarity, which is triangle BLP, is similar to triangle RAP. You can prove all of these similarities by AA similarity. And we'll get BL by RA is equal to LP by AP. This is the fourth result that we have got. Now, if you think about it, from 3 and 4, notice that LP by AP is common there. So we can write simply, one second, I have to minimize this. Right. From 3 and 4, we can see LP by AP is common. So we get CL by SA is equal to BL by RA. And we can write that as CL by BL. CL by BL is equal to SA by RA. And we'll call this the fifth result. CL by BL is SA by RA. And now you can simply do the proof very easily by multiplying the results that you got from 1, 2, and 5. 1, 2, and 5. So let's see what happens when we do that. We'll get AM by MC times BN by NA times CL by BL. I'm multiplying the left hand sides of 1, 2, and 5 is equal to AR by RB. This is the right hand side multiplied by CB by SA multiplied by SA by RA. Notice that SA gets cancelled, RA gets cancelled, CB by RB. Actually, I have made some mistake. It is not AR by RB, it is AR by CB. AR by RB doesn't make any sense. AR by RB. We had similarity of AMR and CMB, right? AMR and CMB. So we said AM by MC is equal to AR by CB. So that is a mistake in writing. I meant AR by CB here. This is AR by CB. So notice now that this is also CP and this gets cancelled. We are getting 1 here. So we have proved that AM by MC times BN by NA times CL by BL is equal to 1. Think about that. Notice that AM is this segment. AM is this segment. Then what is BN? BN is this segment. And what is CL? CL is this segment. So notice that the numerator is the product of alternate segments. And similarly, the denominator is the remaining segments, MC, BL, and NA. So that is the statement of Ceva's theorem, right? So we have proved Ceva's theorem now, and we'll be employing Ceva's theorem now in different applications to show you different sorts of concurrencies, right? So the first simple application of Ceva's theorem is to prove that the altitudes of a triangle are concurrent. How do you prove that? We will draw a triangle here. Let's say this is my situation A, B, C. Let's draw the three altitudes. This is one altitude, this is another altitude, and this is the third altitude, right? We want to show that they are concurrent at H. So according to Ceva's theorem, if I call this D, E, and F, what do I really need to show? By Ceva's theorem, I need to show that the product of alternate segments is equal, right? So I need to show BD times CE times AF is equal to CD times AE times BF. That is what I need to prove for proving the concurrency of the altitudes. Now, this is a pretty easy proof because we can again see similar triangles here. Triangle AFC, for example, triangle AFC is similar to triangle AEB. Why is it similar? Because angle A is common to both. Angle A is common to both. And there is another angle, angle AFC is equal to angle AEF is equal to 90 degree because of the construction of the altitudes. So there are two angles that are common. So by AA similarity, this is similar. And therefore we get the ratio here AB by AC is equal to BE by CF is equal to AE by AF. And you can work with the first and last of these. So you can write AB by AC is equal to AE by AF. This is my result that I get from here. Similarly, you can say that triangle BCF is similar to triangle BAD. Triangle BCF is similar to BAD. Again, because angle B is common and 90 degree is common. So let's write the ratios for BCF and BAD. So we'll say BC in triangle BCF and AB in triangle BAD are opposite to the 90 degrees and then is equal to CF by, here I will say, AD. So I'm getting this result from here, right? And finally, the last similarity that you need is triangle CBE is similar to triangle CAF. What do we get from here? Triangle CBD, CBE and CAF. CAF, correct. CBE and CAF. That is not correct. The CAF is not correct. CBE is similar to what I can say here is similar to CAD. Triangle CAD. Why am I saying that? Notice that there is a 90 degree in the CBE triangle. There is a 90 degree in this triangle. And angle C is common to both of the triangles. CBE also has an angle C and CAD also has an angle C. So let's write the ratios for this one. So we can say by BC by AC is equal to angle opposite to this is BE, side opposite to angle C is BE here, and side opposite to angle C in this one is AD, right? So we are getting this third relation here. So now notice that what I can do is AB by AC here, and there is a BC by AB here. So I should invert this result and I write this as AC by BC is equal to AD by BE. And now I multiply all those three relations. So I get AB by AC multiplied by BC by AB multiplied by AC by BC is equal to AE by AF multiplied by CF by AD multiplied by AD by BE. And this is clearly cancelling out and this is becoming 1. So we have proved that AE into CF into AD, which is AE into CF into AD is equal to AF into AD into BE. AF into AD into B. Okay, maybe I have taken the wrong triangle here. So you have to pick the right triangles. I'm getting the ratio correct. So in the third triangle, I have to take the other ratio. So there are three sides, right? In triangle CBE and CAD, you can take another ratio. So we are getting BC by AC is equal to BE by AD is equal to BC was in this one opposite to angle E, and BE was opposite to C. So what is opposite to this? This is CE by, and in the other triangle CAD, we have opposite to angle A would be CD, right? Correct. So we get BC by AC is CE by CD. So AC by BC would be CD by CE. This is also equal to CD by CE. So instead of AC by BC, I will write here CD by CE. CD by CE. So now what I'm getting? I'm getting CD times AE, and I don't have a BF. So I have to do a similar change of the ratio here. So the point is pretty easy. Like here, we have a similar triangle situation. I have to take the appropriate ratios. I want to prove this. You can try it out. It will come. I just don't want to spend too much time doing this one. You have to take, notice I had written only two ratios. No, take the third side's ratio and use those to prove that these are equal. So try it out yourself. It is not very difficult. You will be able to prove it yourself as well. The second application that I wanted to show you is known as the Gergon point. Gergon point is basically a special point in a triangle. This is basically saying that the lines containing a vertex of a triangle, and the point of tangency of the opposite side with the inscribed circle are concurrent. So what is the meaning of this statement? So the point of concurrency is known as the Gergon point, right? So right now I will explain what is the meaning here. So let's say this is a triangle. Let's say my in center is somewhere here. What is an in center? It is the point of interest, point where the inscribed circle is drawn from. And let's say the inscribed circle is tangent to the sides at these points D, E, and F, right? So basically my in center is I, and the points of tangency are D, E, and F, right? Now what we are saying is the lines containing a vertex of a triangle and the point of tangency of opposite side. So I have to join the vertex A to the point of tangency of the opposite side. So AD. Similarly B with E. So BE. And similarly C with F. CF. And I have to prove that these three lines AD, BE, CF, which are Cevians, are concurrent at some point, at a point. We can call that point as a Gergon point, and I will just label this. So these are my Cevians. This point is G. I have to prove that these lines are concurrent, right? So in order to prove concurrency here by Ceva's theorem, what do I have to prove? BD times CE times AF should be equal to CD times AE times BF, right? This is what I need to prove by Ceva's theorem. Now, it is really obvious if you have done a little bit of properties of triangle you know that this length, this tangent distance is actually s minus b. This is also s minus b. This is s minus c. This is also s minus c. This is s minus a. This is also s minus a. So we can see easily that BD times CE is S minus B times S minus C times S minus A. So left hand side here becomes S minus A, S minus B, S minus C, which is also the same as CD times AE times BF. So it is very easy if you know the distance of the vertices from the point of tangency of the in circle. Now, if you are unsure about how this has come, you should watch a related video that I have posted in my JE 2026 course. Recently, I posted it on YouTube. This is, I think, lecture number 1.7 or 1.8, which talks about the in circle and 4 different formulas for in circle. There we have derived that this distance is S minus B. And this also is S minus B. It's a pretty simple derivation. But right now, what I wanted to focus your attention on is that we can prove that the lines AD, BE, and CF are concurrent, and they are concurrent at a special point which is known as the Gergon point, right? And we have proved the concurrency using Ceva's theorem, right? Now let's look at another special point. It is known as Nagel's point. And this is also similar to what we just now did. Nagel's point is defined as the intersection point or the point of concurrency, intersection point of the lines drawn from the vertices of a triangle to the point of tangency of the opposite ascribed circles. So what is this? What is the meaning of this? Let's think about the ascribed circle. So this is my A, this is my B, this is my C. Let's draw our ascribed circles. How do I draw ascribed circles? I extend the lines, extend the sides, and I bisect the exterior angles. This is my I2, this is my I1, and this becomes my I3. These are the centers of the exterior ascribed circle. So let's say that this is my ascribed circle I2, and this is my ascribed circle here, and this is the third circle, somewhat like this. Obviously, my drawing is not accurate, but it is difficult to be accurate when I'm doing with in hand. What I want you to understand here is this is the point of tangency of the ascribed circle with the side BC. Similarly, this is the point of tangency of this ascribed circle with this side AC. And this is the point of tangency of the third ascribed circle with side AB, right? Now, the intersection point of the lines drawn from the vertices of a triangle to the point of tangency of the opposite ascribed circles. So from A, I will draw a line to the point of tangency of the opposite ascribed circle, which is the I1 circle, right? So this is my CVN here. From B, this is my CVN, and from C, this is my CVN. And I have to prove that this point N exists. N is the intersection point of the three CVNs. Let's call this D, E, and F. Three CVNs AD, BE, and CF. Again, the proof of this is really simple by Ceva's theorem. Proof that these lines actually intersect. The proof is based on, you have to prove that BD times CE times AF again is equal to alternate segment CD times AE times BF, right? If we can show that, the proof is done. And now again, from properties of triangles, you know that this distance, the distance of the point of tangency is actually equal to, of the ascribed circle is actually equal to s minus c, and this distance is actually equal to s minus b. Similarly, this distance would be s minus a, and this distance would be s minus c. And similarly here, this distance is s minus b, and this distance is s minus a. So because of the symmetry, you can easily see that it will again be, the product will be s minus a, s minus b, s minus c. If you are confused about this, again, you have to go back to my properties of triangles video or go to chapter 15, ascribed circles in SL learning. You will be able to easily show that this distance is s minus c, this distance is s minus b, and that will help you prove the result. Now, to end this video, I want to show you one special topic. Here, I will not do the proofs. I encourage you to try the proofs yourself. And what you should try to figure out is, how are these concurrencies happening? These are what we call concurrencies that are determined. Concurrencies determine other concurrencies. So I will give you 5 applications here, and I would leave it for the reader and the viewer to prove. Okay. So what I will say is these 5 situations. So you begin with triangle ABC, and we draw lines, draw Cevians AD, BF, and CE such that they intersect at P. Basically, the 3 Cevians AD, BF, and CE are concurrent at P. Now, consider the circle. Consider the circle that passes through D, E, and F. Through D, E, and F. Obviously, 3 points can uniquely determine a circle. So it is guaranteed that there will be one circle that passes through D, E, and F. And it is likely that this circle also intersects the triangle, intersects the sides of a triangle in 3 other points. You can call them D dash, E dash, and F dash. You can use Ceva's theorem to prove that the lines AD dash, BE dash, and CF dash are also concurrent. That is the statement that I want you to prove. Try it out. Basically, the idea is this. I will just draw a rough figure to explain what this first one is. So let's say we have a triangle here, ABC. Just draw 3 Cevians. This is AD, this is BF, and this is CE. These are 3 Cevians that are concurrent at P. Now, what you should do is draw a circle that passes through E, F, and D. So it will be like a circumcircle like this, right? My drawing is not very accurate, but you should imagine it like this, something like this. So think about it. I have drawn a circle that passes through these 3 points E, F, and D. Notice that the circle cuts the sides again. The same side will be cut again here. This is F dash. This is E dash. And this is D dash. What I want you to show is that A to D dash, B to F dash, and C to E dash is also concurrent, right? The 3 other points that the circle cuts the sides, if you connect it to the opposite vertex and make 3 Cevians, they will also be concurrent. That is what you can try proving. The second application is in triangle ABC, AL, BM, and CN are concurrent Cevians. Draw line segments from M, N, and L such that NR is parallel to AC, where when you draw the line segment NR parallel to AC, R is the point it intersects the other side. Similarly, LS parallel to AB and MT parallel to BC. We have to show the RST here are the points where it cuts the other side. So for example, this is my figure ABC. Let's say this is AL, this is BM, this is CN, and I have to draw LS parallel to AB. So I will draw a line parallel to AB like this. So this becomes my S. And I have to draw MT parallel to BC. So from M, I will draw a line like this. This becomes your T. And similarly, I'll draw NR parallel to CA. So it will be like this. And this will become my R. So we have the 3 points, R, S, and T. And I want to show that AR, BS, and CT are also concurrent. So now using the 3 points R, S, and T, I can prove concurrency of the serials AR, BS, and CT basically. So the figure is complicated to draw, but you can try proving this. Similarly, another application that you can think of for concurrencies is if you have in a triangle ABC, AL, BM, and CN are 3 concurrent serials. Midpoints of AL, BM, and CN are known as R, D, E, and F. And similarly, let MA, MB, MC be the midpoints of BC, CA, AB. You can prove an unexpected result. Prove that the line segment joining DMA, EMB, and FMC are also concurrent. Again, you have to use Ceva's theorem to try to prove this. Think of the triangle DEF here. Obviously, only if you think of the triangle DEF can you think of DMA and EMB and FMC as serials, right? So this is another application. There are several more unexpected results using Ceva's theorem which become obvious. However, that's about it for knowledge about this particular theorem and its applications. In the next few videos, we will explore more results in geometry, more unusual things that you might need to be aware of, and more configurations. So stay tuned, keep watching. I will also be bringing some problem solving videos using actual Olympiad questions in geometry, and hopefully that will also be beneficial to you. So hope you have learned something from this video. If you like the content, please subscribe to the channel, like and share the videos with your friends, and I'll see you next time.